Imagine trying to read like a massive 500-page book, right? But you're only allowed to look at one single word at a time through this tiny, incredibly focused magnifying glass.
Oh, that sounds awful.
Right. It gets worse. You physically cannot skip ahead to see how a sentence ends, and you can't easily glance backward to remind yourself who the characters even are.
You're just totally stuck in the moment.
Exactly. You just have to process every single word in this strict, grueling order, basically just hoping you remember the context by the time you reach the period at the end of the sentence.
Yeah, which is, not how human brains work at all.
No, not at all. But that frustrating, unbelievably slow process, that was essentially how the world's most advanced artificial intelligence used to read and translate human language.
It's wild to think about now.
It really is. But today, we're looking at the exact moment someone shattered that magnifying glass. We've got a revolutionary 2017 research paper from a team at Google Brain, Google Research, and the University of Toronto. And the title is just delightfully simple.
Attention is all you need.
Attention is all you need. I love it.
Yeah.
So if you were listening to this deep dive because you want to understand the exact foundational blueprint that suddenly made AI so blindingly fast and capable, this document is basically the skeleton key. Okay, let's unpack this.
Yeah, let's do it.
Because claiming you can just throw away the established method of an entire scientific field is a massive flex.
It is a massive flex. I mean,
Yeah.
It really is the dividing line in modern machine learning. You literally have the era before this paper and the era after.
Wow, so it's that big of a deal.
Oh, absolutely.
Yeah.
And the reason it's so pivotal is that it proposes a completely new network architecture called the transformer.
The transformer.
Oh,
Yeah.
and the authors basically looked at decades of established computer science and made this wildly bold claim. They said, we can throw away the complex traditional ways computers use to process text and replace them entirely with something called an attention mechanism.
Okay, before we can really appreciate the genius of this transformer architecture, we need to understand the problem it was actually trying to solve, right? Like, why was the old way of doing things broken?
Well, to understand the bottleneck, we have to look at what the industry considered the absolute gold standard at the time for sequence modeling and machine translation.
Which was what, exactly?
That standard relied on recurrent neural networks, or RNNs. Specifically, researchers were using models like long short-term memory LSTMs and gated recurrent networks.
Okay, yeah, I remember that these being the heavy lifters of translation back then. Like, if you used Google Translate prior to 2017, this was basically the engine under the hood, right?
Exactly. They were the best we had, but they shared a fatal flaw, which was sequential computation.
Meaning one after the other.
Right. The way these old models read text was strictly sequential, one word at a time, just like your magnifying glass analogy.
Right.
The neural network would generate what's called a hidden state for a given word, which is, well, it's basically a snapshot of its current understanding of the text.
Okay, a snapshot. Got it.
But that calculation depended entirely on the hidden state of the previous word.
Ah, okay. So I picture it kind of like an old school factory assembly line.
Now, that's a good way to look at it.
Yeah, like you have a long row of workers, right? And worker B physically cannot start their job until worker A is completely finished, hands over the part, and passes along the instruction manual.
Yes, exactly.
So if you have a really long sentence, the worker at the very end of the line is just sitting there twiddling their thumbs, waiting for the context to make its way down the conveyor belt.
That is a great way to visualize it. And the problem with an assembly line is that it makes it physically impossible to do multiple tasks at the exact same time. You literally can't process the whole sentence at once.
But wait, looking at the research here, researchers obviously knew this was a problem, right? The paper mentions things like factorization tricks or conditional computation.
They do, yeah.
Didn't those help speed things up before 2017?
I mean, they did improve computational efficiency to a degree, but think about your assembly line analogy. Those tricks were basically just giving the individual workers a bunch of caffeine so they could move their hands a little bit faster.
Oh, okay. So the line is still there.
Exactly. The fundamental constraint was still there. You still couldn't process the text in parallel. And when sentences get really long, or you try to analyze a whole paragraph, memory constraints become a massive issue.
Because you're holding on to too much stuff.
Right. You are generating all these hidden states along the way, carrying all this baggage down the line, and the computer simply runs out of short-term memory.
Which means if you can't compute in parallel, you just can't scale up without waiting forever or needing like an impossible amount of computing power.
Exactly.
And Honestly, anyone who used early translation software remembers the result of this bottleneck. You'd put in a paragraph, the system would lose track of the subject by the third sentence, and it would just spit out total word salad.
Yeah, the classic translation fails.
So the researchers needed a way to look at a whole sequence at once without losing the context of the sentence. Enter the transformer.
Right. The researchers essentially looked at the assembly line and said, what if we just tear down the factory entirely?
Just scrap it.
Scrap it. Their radical proposal was to get rid of recurrence entirely. No more sequential hidden states.
Wow.
Instead, they relied solely on something called self-attention, or intra-attention, to draw global dependencies between the input and the output.
So what does this all actually mean? If we aren't using the assembly line anymore, how does the model actually understand the text?
Well, let's
Actually, let me try another analogy. Tell me if this works.
go for it.
Instead of whispering a message down a sequential line of people, like a giant game of telephone where the word slowly gets passed along, self-attention is like being at a really loud, crowded dinner party.
Okay, I like this.
You can hear everyone in the room speaking simultaneously, but your brain instantly calculates exactly who to pay attention to based on how relevant their words are to the conversation you care about right now.
That's perfect.
So you process the whole room at once, but you weight the importance of each voice.
That captures the dynamic perfectly. In the paper, this process of figuring out who to listen to at the party is achieved through what they call scaled dot product attention.
Scaled dot product attention.
Right. It's the core engine driving the transformer.
Clear.
The mechanism takes the data and maps a query and a set of key value pairs to an output.
Okay, let's slow down here. If I'm looking at this query key value setup, my brain immediately goes to an old metal filing cabinet.
A filing cabinet, okay.
Yeah, tell me if I'm off base here. The query is me. I'm holding a piece of paper looking for a specific tax document. The key is like the sticky note or the label on the outside of the folders in the drawer.
Right.
And the value is the actual financial data inside the folder. Is the AI doing something like that?
It's very similar, yes. Let's map your filing cabinet to a sentence. The query is the current word the model is trying to understand.
Yeah.
The keys are the labels representing all the other words in the sentence. And the values are the actual underlying meanings of those words.
So the model takes its query and it simultaneously checks it against all the keys in the sentence to see what matches.
Exactly.
But wait, how does it measure a match? Is it just looking for identical words?
No, it's looking for conceptual relevance. Mathematically, the model computes the dot products of the query with all the keys.
A dot product.
Yeah, a dot product is really just a mathematical way to calculate a similarity score between two lists of numbers. High similarity means a high score.
Got it.
So a word checks its query against the keys of every other word in the sequence simultaneously and generates a massive list of similarity scores.
Okay, but the paper explicitly calls it scaled dot product attention. If you are listening to this and your eyes are kind of glazing over at the term scaling dot products, hang with us for a second because I really want to ground this in reality. Why did they need to scale it?
Because of the sheer size of the numbers involved.
Like, how big are we talking?
Well, the model represents these queries and keys as long lists of numbers, specifically 64-dimensional vectors.
Whoa, wow.
Yeah. And when you multiply lists of numbers that long together, the resulting similarity scores can grow astronomically huge.
So the AI just gets paralyzed by huge numbers. Why is a big number a problem?
Because the very next step in the process is to apply something called a softmax function.
Softmax.
Right. You can think of a softmax function like creating a percentage pie chart.
Okay, I can visualize that.
It takes all those similarity scores and squashes them down into a neat set of probabilities that add up to exactly 100%. It tells the model, pay 60% of your attention to this word, 30% to this one, and 10% to that one.
Ah, I see. That makes sense.
But here's the issue. If you feed massive extreme numbers into a softmax function, it breaks. The function gets pushed to its absolute edges, where the gradients, the signals it uses to actually learn, become incredibly small.
Oh, so it just stalls out.
The math essentially stalls out, yeah, and the model completely stops learning. So the researchers added a brilliantly simple fix. They scaled it.
How so?
They took those giant similarity scores and simply divided them by a specific number, the square root of the dimension size.
Oh, okay. So just shrinking it down.
Exactly.
Okay.
By dividing it, they shrank the numbers back down to a manageable size, keeping the learning process healthy and efficient. Then, and only then, they apply the softmax pie chart and multiply it by the values.
That is such an elegant way to keep the math from eating itself.
It really is.
But hold on. Being able to look at all the words at once using this query key value system is great, but human language is notoriously messy.
Oh, extremely messy.
Right, like words have multiple layers of meaning simultaneously. There's grammar, there's the subject, there's the tone of the sentence, the emotional weight.
Yeah.
If you just do this attention calculation once for the whole sentence, how does the model capture all these different nuanced relationships without the signals just blurring together into a muddy average?
That was a major hurdle. You're exactly right. If you only have one attention mechanism, it tends to just average everything out into this sort of generic representation.
Right.
Their solution is what they call multi-head attention.
Multi-head attention.
Yeah, instead of performing just one giant attention function on the data, the transformer projects the queries, keys, and values multiple times. Specifically, in this base model, they use 8 parallel attention layers running at the exact same time. They call these layers heads.
Okay, here's where it gets really interesting. Let me throw another analogy at you to see if we can visualize these 8 heads.
Let's hear it.
Imagine you have a really complex classic painting. If you hire one general art critic to look at it and analyze the color, the composition, the historical context, and the brushstrokes all at the exact same time, they're going to get overwhelmed.
Definitely.
Their review will just be a muddy summary. So instead, you hire 8 specialized critics to look at the painting simultaneously. But to make sure they don't get in each other's way, it's like each critic is given a special pair of glasses.
I like this.
Critic A's glasses filter out everything except the color red. Critic B's glasses only show the physical texture of the paint. Does that track?
That analogy actually maps perfectly to the math they used.
Really?
Yeah. The paper states that multi-head attention allows the model to jointly attend to information from different representation subspaces.
Representation subspaces.
Yeah.
Okay, so those are my specialized glasses.
Exactly. Those subspaces are exactly like your specialized glasses.
Right.
By projecting the data into these different mathematical filters, one attention head might learn to focus entirely on grammar-like linking verbs to nouns.
Oh.
Another head might put on a different pair of glasses and focus entirely on resolving pronouns, figuring out who he or she refers to earlier in the text.
Because they are operating in parallel, the model just extracts all these different layers of meaning simultaneously without washing them out.
Exactly. It calculates the attention for all 8 heads,
Yeah.
stitches the results together, and just moves forward.
It makes so much sense when you frame it like that. But I have to push back here on a glaring issue I'm seeing.
Sure. What is it?
If we throw away the sequential assembly line reading of the text and we process all the words in parallel in a giant cloud of attention,
Right.
how does the model know the order of the words?
Wow.
Like, think about it. The dog bit the man and the man bit the dog have the exact same vocabulary. They would have the exact same keys and values, wouldn't they?
They absolutely would.
So if they are processed simultaneously, how does the AI know who ended up with a bite mark?
That is the exact problem you introduce when you remove recurrence. You completely lose the inherent concept of time or sequence order. A bag of words is just a bag of words to a computer.
Right.
To fix this, the researchers had to artificially inject information about the position of the words directly into the data before the attention mechanism even starts. They call it positional encoding.
Positional encoding. Okay, but how do they actually inject it? Did they just slap a number 1, 2, 3 next to the words?
It's much more sophisticated than just adding a whole number. They use trigonometry.
Wait, what?
Yeah, specifically sine and cosine functions of different frequencies.
Wait, hold on. You're telling me they solve a language sequencing problem using trigonometry, the stuff with the triangles from high school.
That's the one.
But if you just add a geometric math wave to the word dog, doesn't that fundamentally corrupt the data? Doesn't it change what the AI thinks the word dog means?
I mean, it's a highly counterintuitive concept, I'll give you that. But it works because of the sheer size of the mathematical space we are operating in. Remember those 64-dimensional vectors?
Yeah.
The word dog is defined by a massive array of numbers. The sine and cosine waves are added to that array, but they use a geometric progression of wavelengths. What this does is create a unique, continuous mathematical signature for every single position in the sequence.
A mathematical signature.
Yeah, it's like applying a very subtle, invisible watermark to the word.
Oh. Okay, so position 5 has a specific sine wave watermark, and position 10 has a completely different one, but the core meaning of the word dog remains intact.
Yes, exactly.
Yeah.
They hypothesized that using these sinusoids would allow the model to easily learn to attend by relative positions because, for any fixed offset, The positional encoding can be represented as a linear function of the previous position.
That means,
To put it simply, it gives the model a built-in mathematical ruler. It can perfectly measure the distance between any two words, regardless of whether the sentence is 5 words long or 500 words long.
okay, I have to admit, the theory is undeniably elegant.
It is beautiful math.
We've thrown out the slow assembly line. We're using self-attention to read the whole sequence at once. We have 8 specialized art critics capturing different nuances, and we are using sine waves as a built-in ruler to remember the order of the words.
That's the transformer in a nutshell.
But theory in computer science is just theory until you run the code. Did this parallel attention-only architecture actually perform better than those heavy-duty recurrent neural networks in practice?
The results were, honestly, nothing short of a paradigm shift. The researchers tested the transformer on the standard WMT 2014 translation tasks.
Okay.
These were highly competitive, standardized benchmarks that the entire industry used to measure progress. On the English to German translation task, their big transformer model hit a new state-of-the-art BLEU score of 28.4.
Let's contextualize that for the listener, because just throwing out the number 28.4 doesn't mean much on its own.
True.
In the machine learning community, researchers were fighting tooth and nail for a 0.1 or 0.2 increase in a BLEU score. So what does a 28.4 represent here?
It represents a massive leap over the competition.
Yeah.
This single model beat all existing best results by over 2 full points.
2 full points.
Yes, and that includes beating massive ensembles, which are giant clusters of different models working together to boost a score. It's essentially the equivalent of a runner suddenly beating the 4-minute mile by 30 seconds on their first try.
That is insane.
And they didn't stop there. On the WMT 2014 English to French translation task, it established a new single-model state-of-the-art score of 41.8.
That is a staggering jump in accuracy, but honestly, looking at the paper, the accuracy isn't even the craziest part to me. It's the efficiency.
Ah, yes, the compute.
Because they removed that sequential bottleneck, because they didn't have to wait for worker A to hand a part to worker B. The training cost just plummeted.
Absolutely plummeted.
Previous state-of-the-art models required massive computational power, pulling numbers on the scale of over 1 billion floating point operations. The big transformer model dropped that computing cost down to a fraction of the previous heavyweight models. It trained in just 3.5 days using 8 standard GPUs.
And their smaller base model achieved fantastic results in just 12 hours.
12 hours?
Yeah. Previous state-of-the-art models from the literature often took supercomputers running for weeks or months to achieve worse results.
Which is incredible. But, we've talked about how fast and cheap this model is and how accurate the translation was. But speed and accuracy don't matter much if we don't know what it's actually learning.
Right.
Did this math just create an incomprehensible black box? Or can researchers actually see inside it?
What's fascinating here is that we can actually look under the hood, because the model uses those attention weights, literally assigning a percentage of focus from one word to another. We can visualize exactly what the model is thinking.
Oh, really?
Yeah, the researchers inspected the attention distributions and included these beautiful visualizations in the appendix of the paper.
And looking at these visualizations, it proves that those 8 different attention heads, our specialized art critics, actually learned to perform recognizable linguistic tasks entirely on their own.
Completely on their own.
Nobody fed this thing a grammar textbook. Nobody explicitly programmed it to know what a pronoun is.
They just let it read. Let's look at layer 5 of this 6-layer encoder stacks on the paper. In one example, they show 2 specific attention heads involved in anaphora resolution.
Anaphora resolution.
Yeah, that's just the linguistic term for figuring out what a pronoun refers to. The sentence they fed it was, "The law will never be perfect, but its application." And when you look at the attention weights for the word "its," the model is sending a massive sharp spike of attention directly back to the word law.
Wow.
It completely understands the structural dependency there.
It's not just looking at the words immediately next to it then. It is leaping backward across the sentence to grab the exact context it needs. There's another example in the appendix that shows long-distance dependencies, which were, famously difficult for the old assembly line models. The sentence fragment is making the registration or voting process more difficult.
Oh, that's a great example.
Right. The visualization shows the attention mechanism perfectly bridging the gap across a wide span of text. The verb making is sending strong attention directly to the phrase more difficult. It completely bypasses all the clutter of the registration or voting process sitting in the middle.
If we connect this to the bigger picture, the model is dynamically routing information based on the actual semantic and syntactic structure of the sentence, rather than just reading strictly left to right.
Right, it breaks out of the linear constraint.
In mathematical terms, the path length that forward and backward signals have to traverse drop to a constant time. To translate that, instead of taking a slow train that have to stop at 50 different stations to get a message across a paragraph, the transformer takes a direct, non-stop flight between any two words. It makes learning these long-range dependencies infinitely easier than it was for the old RNNs.
So, to summarize the journey we've been on today, we explored how a group of researchers looked at the slow, sequential assembly line of neural networks, realized it was an artificial bottleneck, and just threw it out completely.
Trashed it.
They replaced it with parallel, multi-headed self-attention. They created a system that could look at an entire sequence at once, understand the myriad connections between the data points simultaneously using specialized filters, and keep track of the word order with a genius mathematical ruler made of sine waves.
And by solving that computational bottleneck and making training vastly more parallelizable, this specific paper essentially democratized sequence modeling. Well, you didn't need an infinite budget to play in this space anymore. It generalized incredibly well, too.
Mm.
The researchers showed it performed brilliantly on entirely different tasks, like English constituency parsing, where the output is subject to strong structural constraints, even with limited training data.
Wow.
They unequivocally proved that attention truly was all they needed.
Which leaves you, the listener, with a fascinating, lingering question to mull over. The researchers proved this pure attention mechanism is unbelievably efficient at mapping the complex sequences of human language. It learned grammar, syntax, and meaning just by paying attention to the relationships between data points.
Right.
But if attention is all you need to decipher the complex rules of a sequence, what happens if we apply this exact same architecture to other complex sequential codes in our universe?
Oh, that is a big question.
Right. If it can translate English to German by understanding the hidden structure, could this exact same self-attention model eventually be used to translate sequences of audio, the visual frames of a video, or even the genetic sequencing of our own DNA?